All right, hi everybody. We're going to add what we call our co-function identities into our list of identities that we've been working on, and I'm including this in the same section as our sum or difference identities. And really, there's three different ways that we can think about these identities, and it's worthwhile because we start to see these different connections happening. So let's take a look and see what it says. Our first one, the sine of x equals the cosine of pi over 2 minus x. And let's think about what this means here. And I'm going to switch to thinking about degrees here for my first thought with this. Pi over 2 is 90 degrees, right? So we're saying that the sine of an angle is equal to the cosine of 90 degrees minus that angle. And I first want to go back to this last example from the previous video. What did we say here? We noticed that the sine of 75 degrees equals the cosine of 15 degrees. We used sum and difference identities. We first did the sine of 75 degrees, and we found out it's the square root of 6 plus the square root of 2 over 4. And then we did the cosine of 15 degrees using a difference identity, and we found out it's the same exact thing, the square root of 6 plus the square root of 2 over 4. So the sine of 75 degrees equals the cosine of 15 degrees. And my first thought with this cofunction identity is to think about a right triangle. And I think about the relationship between those two angles in the right triangle. So let's sketch a right triangle. And let's say that this is 75 degrees. I know I didn't draw it like 75 degrees, but let's just say that's 75 degrees. And let's just label our triangle here as A, B, and C. What is the sine of 75 degrees? It would be opposite over hypotenuse, A over C. Okay, now I know we know exactly what that is, but I'm just throwing generics in here. Now, what if we switch to a 15-degree angle? Well, I hope you'd notice that if this is a right triangle, we've got 90 degrees there, we have 75 degrees there, that leaves 15 degrees here. What is the cosine of that angle 15 degrees? Well, the cosine is going to be adjacent over hypotenuse, and with this angle, the adjacent is A, and the hypotenuse is C. So we end up with the same ratio. The sine of 75 degrees is equal to the cosine of 15 degrees. They're the same ratio. They're both A over C. Now we can generalize this a bit more and say, you know what, let's not look at 15 degrees and 75 degrees. Let's call this x degrees. So then the sine of x equals A over C. Then what's this angle? Well, that angle is 180 minus 90 minus x, or just 90 minus x. And what's the cosine of 90 minus x? Also A over C. So we get the same thing. And we just wrote this here in radians instead. Instead of 90 degrees, we have pi over 2. So that's my first way of thinking about it is, of course, this makes sense because we're looking at two complementary angles, okay, that have to be in the same right triangle, and we're just switching what angle we're looking at, and we're changing from sine to cosine, and so on. So that's my first way to look at it. My second way to look at this would be to tie it back to our sum and difference identities and actually verify that this is true. So can we verify that this is true using a sum or difference identity? Because what do we have right here? We have a difference, don't we? So let's start with the right side, the more complicated side, and see if we can simplify it and just get the sign here using our difference identity. So I've got that my difference identity right here. Where is it? There it is. All right, so the cosine of u minus v, and I'm just looking at a different way of writing it because here we use x's and y's instead of u's and v's like the example I'm looking at here. But the cosine of x minus y is cosine of x cosine of y plus sine of x, sine of y. So this would be cosine of pi over 2 cosine of x plus sine of pi over 2 sine of x. Just double checking my identity. Cosine, cosine, plus sine, sine. Okay, there we go. Now, take a look at this. What's the cosine of pi over 2? Well, where are we looking at on the unit circle? That would be at the top, wouldn't it? Okay. So, the cosine of pi over 2 is 0. Okay, now that's just an x, so we'll just leave it. Sine of pi over 2, again, we're at the top. And what's the value of the sine of pi over 2? Well, that is 1. And when we take a look at this, what's 0 times cosine of x? That's 0, of course. 1 times sine of x is sine of x. So we have 0 plus the sine of x, which is the sine of x. And we have just proved that cofunction identity is true. So that's my second way of looking at it. Let's go with one more. When I look at this, okay, I can't help but think of transformations of graphs, right? This looks a lot like a transformation of a graph, and let's think about what that transformation would be. And I'll actually pick the second one here to take a look at this. The cosine of x is the sine of pi over 2 minus x. So I have graphed cosine and sine. And we know when we look at these graphs that they are just horizontal transformations of each other. So I might be tempted to say, well, they're just transformations of pi over 2. So what if I just take x minus pi over 2? Do they match up? And the answer to that, of course, is no, they don't. They don't match up. That's because I did pi over 12. There we go, pi over 2, that looks better. They don't match up, okay? They are actually reflections of each other. That's because I actually transformed in the wrong direction. I could, instead of transform to the right pi over 2, if I do a plus pi over 2, okay, now they match up. But let's go back to the minus, because our cofunction identity has a minus in it. These don't match up. However, okay, this is not the way that our cofunction identity is written. It's not x minus pi over 2, it's pi over 2 minus x. And the reason for that would be when we look at these aren't matched up, but they're reflections of each other. So if I perform a reflection, okay, and I put it there, now they match up. But again, this is not the same way that our cofunction identity is written, because it doesn't have a negative out front. However, when I see a negative out front, I think of even in odd functions. And we know sine is an odd function. So I can actually put that negative inside, because the sine of negative x equals the negative sine of x. So instead of thinking about reflecting it over the x-axis, I can think about reflecting this, okay, by putting the negative inside. Like that. Now it matches up, doesn't it? But this still doesn't look the same way that this looks. It doesn't say pi over 2 minus x. We have negative x minus pi over 2. Well, what happens if I distribute that negative? I have negative x plus pi over 2, same graph, and then we're just switching the order that we write it. Okay, there we go. So that's my graphical approach. So first way I thought about the cofunction identity is by looking at a right triangle and looking that we're just switching between the complementary acute angles in a right triangle. The second way is to use a sum or difference formula to verify it. And the third way is to think about what the graphs look like. And I think that's a brilliant way to really show our mathematical minds at work. We're trying to understand something in multiple ways, connecting it to different things that we already understand. So that's terrific. So when we take a look at these cofunction identities, just last comment, Sine and cosine, they look pretty much the same, don't they? We've just switched where the trig ratios are. Tangent, of course, is different because it's always different. The tangent of x equals the cotangent of pi over 2 minus x. I would like you to consider that a little bit. Take some time thinking about it. I'm not going to do it in this video. Last thing I want to do with this is let's just do a quick example here. What if I wanted to find the sine of 170 degrees, but in terms of cosine instead? Well, we know, looking at this identity, that the sine of x equals the cosine of pi over 2, which is 90, minus x. So I can just say this is the cosine of 90 degrees minus, what's our x on this one? 170. So that tells me the sine of 170 degrees equals the cosine of 90 minus 170 would be, what, negative 80? Yep, there we go. So that's just one way that we can use that. All right, let's wrap up this video by doing one more verification of an identity or proving an identity. This time we're going to put into use some of the identities that we have looked at in this section. So let's prove that the sine of, let's throw a little bit of Greek letters in here just for fun. No, not just for fun. You have to get used to it. They show up sometimes. The sine of alpha minus beta over the cosine of alpha cosine of beta. So again, this is alpha, this is beta. That's how you say them. The sine of alpha minus beta over the cosine of alpha cosine of beta equals tangent of alpha minus tangent of beta. So can we prove that? One of my hints again has been start with the more complicated side. I would say that's the left. When I look at this, I'm not really sure what to go with, except I do notice that I have a difference within that sine angle in the numerator. So let's use a difference identity for sine. The difference identity for sine would be sine cosine plus cosine sine. So this is going to be sine alpha cosine beta. Remember that the sine stays the same with sine minus cosine alpha sine beta. That's our new numerator using the difference identity. In the denominator, we have a cosine of alpha cosine of beta. I'm sorry my equal signs didn't line up here. I'm just going to go with it looking at the clock. I don't have time to mess with that. All right, so I've now switched this. I feel better about it. If I look at the right side, there's just alpha and beta as an angle. There's no difference of angles in there. So I feel better because all my angles are just alphas and betas, no alpha minus betas. Let's see, now what? Again, peeking at the end here, I have tangents, and I know tangents are sines over cosines. So can I get sines over cosines here? Well, we do have a fraction, and we have sines and cosines in the numerator, and we have cosines in the denominator. So I feel good about that as well. Here's what I would recognize. I am subtracting in the numerator. Well, if I do the reverse of subtracting fractions, I can split this up into two different fractions with a common denominator. Like that. Now, my numerator would then have to be that. Okay, so because I'm subtracting the numerators, right, we keep the denominator the same, we subtract the numerators, that matches up. We will now notice that the cosine of betas cancel. We have a sine of alpha over cosine of alpha, which is a tangent of alpha, minus here the cosines of alphas cancel. We have a sine of beta over cosine of beta, which is a tangent of beta, and we have just proved this identity. All right, so some new things to think about with our cofunction identities. I really enjoyed our thought process on that. Here is one more example of verifying an identity for you guys. Thanks for watching. We'll see you later.